Wednesday's little quiz? Yeah, maybe? Quiz? Wednesday? Tuesday? Wednesday, when you want it? Wednesday. Tuesday?
No, Wednesday.
Wednesday, yeah, just over chapter 1, right? Yeah. Just the notepad, the outline, just like the outline is good. Yeah, I'll give you some sample questions today. And then what do we have on Thursday? Yeah, your first lecture test on Thursday. It'll cover through whatever we finish tomorrow. That'll be the information you're required to know through tomorrow. Then like Wednesday, we'll review, finish some more stuff. I won't test you on anything other than what we cover through tomorrow. So we have time to go home and review, ask questions on Wednesday, and then go from there. I like to want to give you stuff like on Wednesday and then test you on Thursday. Seems to like, so we'll do it this way. All right, good. I think we left off on here, right? Just a trainer, whatever. So perfect. All right. So we were talking about different types of compounds a little bit. We did molecules and compounds and the atom. We talked about protons and electrons and neutrons and isotopes and all that crazy stuff, the radicals. So now we're going to take a look at organic versus inorganic compounds. So if you remember by definition of a compound, it had to have 2 or more different atoms, right? So just like a quick little review. So like carbon,
again.
a carbon atom, hooked to a hydrogen atom, is that a compound?
Yes.
It is, because they're different, right? What about 2 oxygens together? It's just a molecule, right? Okay, so now we're going to do inorganic compounds. So we're taking 2 or more different atoms and stringing them all together. So the key of this one is, it says what? It does not contain carbon. We want to write in there, maybe it does not contain carbon as the primary structure. That's probably better. Does not contain carbon as the primary structure. These things are going to be very, very, very simple in nature. Meaning, I don't know, here's some examples. Water. Okay, let's take a look at water. We know water is oxygen with how many hydrogens? 2. 2, okay. And then I have, I don't know, a salt, like sodium, but to chlorine. Again, 2 atoms, right, of different things. What's acid? Anybody do acid?
Hydrogen.
All right, so you need a little bit of hydrogen with some chlorine, like hydrochloric acid, used for your swimming pool, right? Right, John? Hydrochloric acid. And a base, like, I don't know, sodium. And we can do like a little hydroxide on it, sodium hydroxide. So they're really simple in their structure. 2 or 3 atoms put together. So, as it says, right, very simple structures. Doesn't contain carbon as the primary structure, primary chain. So we're going to talk about each one of those and give you some examples of that, what they are, and how they work, and why we need them in the body. So again, these are inorganic. Inorganic does not contain carbon. All right, good. So let's run through and do a few of those. And we're going to start with water. First, I'm thinking. It says it's the most important inorganic compound in our body. Remember, like the other day, we said 65% of the body is made up of like oxygen, and then we got hydrogen. Okay, that's good stuff. So we have to have water for many, many, many different things in the body. It keeps us cool, for proper metabolism and things like that. How much water should we drink during the day? It's like pure water.
A gallon.
Yeah, like nobody has like the right, so it's going to be about 8 glasses, a gallon, or whatever.
40 ounces.
All right, so look at it this way. If you weigh 100 pounds versus somebody who weighs 400 pounds, you drink the same amount of water or a different amount of water? Different, right? So everybody's different. Here's a good rule of thumb. Take your weight and divide by 2, and that's how many ounces of water you should drink per day. Ounces. Yeah. So if you're 400 pounds, you should drink 200 ounces per day. So most of you guys like what? Like 130 to 180? Except for females, right? You guys like what, 115 maybe? Right. So yeah, you want to do about 75 ounces per day. Men, you want to do about 90 ounces per day. Right?
Still about a gallon.
In that range, 75. Yeah, so you're close to that gallon, right? 128 per gallon. So yeah, so you got to stay hydrated. Okay. So anyways, keep that in the back of your head maybe. Drink some more water. Does Coke count as water?
No.
Because there's water in it. Yeah. That's actually pure water. Tea,
No.
coffee, that is water, pure
What about
water,
herbal
right?
tea?
Yeah, yeah.
What about green tea?
So there's nothing, just water. Green tea is good for you.
Yeah,
but-
I mean, just put a regular green tea, I'm not talking about the bottled stuff.
Yeah, green tea actually is really good for you. Okay, here are some properties of water. Okay, so we're going to go through just some properties of water, the functions of water, and all that crazy stuff. So it says that water is a great solvent. Water is a great solvent. So, like, what the heck is a solvent? It dissolves something. Okay, so it's like, I know, that guys have like nail polish. How do you get nail polish off? With
Nail polish
remover or acetone, right? So it's a solvent. It dissolves nail polish. So water is used the same way in the body. We can break things apart using water. So we say it's a solvent. So useful to dissolve both organic and inorganic compounds. We don't care about that. But do know those two terms, hydrophilic and hydrophobic. So I always say if you can like break the word apart, you can like figure out what the heck you're asking for, right? So hydrophilic. You guys have like medical terminology yet? Probably not, right?
No.
That's hydrophobic. Yeah, so if you break those words apart, it just means pertaining to, right? So that's just pertaining to. Hydro means water, and Phil is it's a guy, right? Like Phil, Dr. Phil. That means love, right? So water loving, right? Pertaining to water loving. And if you have a phobia, you have a fear. So hydrophobic is you're afraid of water. It's when you like water. Okay? Fear, like, okay. So hydrophilic, we like it. Hydrophobic, we fear it. What about oil? Does oil and water mix very well?
No.
Yeah, okay, so it doesn't mix so good. We're going to find we can use some water to help us break things apart, like carbohydrates and proteins and things like that. So it really is like two definitions for you, hydrophilic and hydrophobic. Okay, that's my water thing so far. We're going to do solutions, solutes, and solvents coming up next. Solutions, solutes, and solvents. You guys like Kool-Aid?
No.
You eat Kool-Aid. This is my example. I use Kool-Aid for doing my little water picture here. Okay, we're going to make Kool-Aid. What type of Kool-Aid do you guys like? I don't know.
Grape, cherry.
It's like boring. It's like purple dinosaur Rex Kool-Aid. Alright, so we're going to dump in our purple dinosaur Rex color Kool-Aid over here. So purple Rex, what's called purple Rex. Okay, and then to add sugar too, right? How much sugar do you put in?
A cup.
You guys make boring Kool-Aid. Like 3 cups, right?
Oh.
3. It's like way better than more sugar. So we're
It's
putting
true.
3 cups of sugar. Whatever. Alright, then we're going to mix it with water, right? Yeah, okay, alright, so here's the deal. Here's what we're going to have. To make a solution, and when I mix all this stuff together, it's called a solution. That's my final product, is a solution. Solute is the stuff that dissolves in water. So that's my sugar and my purple dinosaur mix. That's my solute. Then what's the solvent then? Water. We just said water is a solvent. It dissolves things. So water mixes with the sugar and the purple dinosaur Rex color through there. We mix it all together to make our final solution. So again, the solution is the final product. Water is a solvent, and the solutes are the things that are being dissolved, i.e. the sugar and the purple dinosaur Rex color Kool-Aid. Okay, while we talk about that, because we're going to have a few things, like in the body, we have to talk about. You guys want like a definition of that, or you guys are okay? So solvents dissolve particles. We'll do it like backwards. So solvents dissolve particles, known as solutes. Okay. And solutes are the particles that are being dissolved. And when you do that whole little mixture, it's known as a solution. And we're going to find a little later on that we had to have a certain solution for starting like IVs on somebody, because you didn't make sure that you put in the right amount, right? Otherwise you kill the person. So it's sort of like an important thing to know about those solutions. What the solvents, okay, so we'll do more of that a little bit later on. Okay. Tipping right ahead here. Maybe. Maybe not. Great. Here we go. Alrighty. So we're rocked up there for a minute. I'm sure everyone can see anything. Yeah, here we go. Okay. So we know water's a great great solvent, and we can make solutions with it. Also, it says that I need water for chemical reactions to occur as well. Two more words for you, hydrolysis and dehydration. So if you take that word apart again, here's that word hydro. That meant water. And what if you lyse something? You cut it, right? You break it apart, you cut it. So hydrolysis, this means we break things apart using water. So we break things apart using water. So that would be a chemical reaction. We're going to break something apart using water, and we're going to find that we're going to add water to decompose that thing or to break it apart. Now the flip side of that is I have something known as dehydration. What happens if you dehydrate? You lose water, right? So water's going out. So it says here water molecules are removed from, right, that substance or whatever during a reaction for us. So again, this has to do with like chemical reactions, right? Adding water, taking water out, things like that. So if I have my, I don't know, what do you guys want to break apart? A Twinkie? Sure. Put a Twinkie on there. It's like known like good stuff with the Twinkie, right? It's like all man-made chemicals. Do you guys ever see that? Like made in the lab, Twinkie. It's like no natural food products and etc. You like leave a Twinkie on your dashboard for like 30 years. It's exactly the same as it was from like day one. It has like no half-life. Yeah, they're just like they are. Yeah, Twinkies like crazy up. Anyways, so we can like use some water. So we're gonna add some water to break our Twinkie apart. Yes, right. Your little things. That'd be my little hydrolysis reaction. And then again, if I take water out, going the other way, it would be a dehydration one. Alright, so good on that. Water used for chemical reactions. Used for chemical reactions. Water also has a very high heat capacity. What the heck does that mean? High heat capacity. Yeah, you can absorb a lot of energy without changing the temperature too much. That little thing of like, I don't know, you have a pot of water and you put it on your burner. Like how long before your water starts to boil? Yeah, like a really long time, right? It's to reach that 100 degrees Celsius thing or 212 degrees Fahrenheit, whatever. But all the energy from the little burner going up into your pot of water, it takes forever for that water to boil, right? Like a watch pot doesn't boil something. So the water absorbs all the energy without changing temperature too much itself. So we say it has a very high heat capacity. Works out great for things like your car radiator, right? With like antifreeze and water. So all the heat from the engine. Otherwise your car would overheat if you don't have water in the radiator. And same thing for the body, we would overheat as well if we don't have water inside of us too, right? So all the chemical reactions that are occurring inside the body generate a lot of heat. Therefore we start to perspire and sweat to help us maintain that body temperature. So we gotta have water inside. So, as it says, water can absorb a lot of heat and store a lot of heat without changing temperature too much itself. So it's a great coolant for the body, right? So water's a coolant. Helps us maintain that constant body temperature. Good for that? Not bad, right? So water's a coolant. Also, we have something known as a high heat of vaporization. What the heck is that? High heat of vaporization. What if something vaporizes?
Changes to gas.
Yeah, it changes, right? So, okay, here's like a great example. So it evaporates, right? So vaporization, evaporation sounds something the same. So we have like water on the ground, it evaporates, right? Goes to a different state. Think about this, like you take a shower and you step out of the shower, are you hot or cold? Usually.
Cold.
Or out of a swimming pool or out of whatever. Usually a little cooler, right? So what happens is all the water that's on your body from your shower, from the swimming pool, from the hot, whatever you're in, right? It evaporates. When it evaporates, it pulls the heat out of your skin. That's how sweating works for you too. That's how we cool the body down using sweat. So you're outside, you're working, you're generating a lot of heat because your muscles are working. All those chemical reactions are burning you up inside. You start to perspire, the water's on the surface of the skin, the water evaporates and pulls the heat out of the body. That's why you have to sweat to cool the body down. Otherwise you burn up. So we say it has a very high heat of vaporization as well. So make the body